All right, let's have a look at resistance. Again, seems a really basic concept, and it's not. But let's just go over what we do remember. We all know Ohm's law, used it heaps. V equals IR, and again, I don't necessarily even like this because I think we've already learned that voltage, if you looked at my first little video, can emanate from, or does emanate from, a charge. So you've got a negative charge there, then you've got a voltage. At this point here, you've got a voltage. Where's the current? Where's the resistance? And yet we found, so that voltage formula is like what we find works in circuits. So we'll talk about that. We did talk about this as Ohm's law, and what we said was that with Ohm's law, if you wanted resistance and you had a graph and you plotted voltage over current, then voltage divided by current equals resistance. So the gradient of this graph here would be your resistance, and it's a nice straight linear function. So we call that an ohmic conductor. I think we all know now that conductors have a very, very low resistance and insulators have a very, very high resistance, and it's all because of free electrons, right? So if we had a resistance that was increasing, so it starts off nice and straight, but then it starts to go like that. The gradient, this is voltage against current, the gradient's increasing, so what we would call that is a non-ohmic conductor. And since the resistance is increasing, we could ask ourselves why, and this is one of the situations where you might go, well, okay, what happens when the voltage goes up, the current goes up? Well, the power goes up, the temperature, there's a lot of heat, temperature goes up, and that can affect resistance. So this would be the non-ohmic. In year 12 or level 2, you look at diodes and things like that too, a little bit, which have resistance, low resistance one way. You looked at this. The arrow pointed from positive to negative. You had low resistance if you went that way, but you had a high resistance if you went that way. So this whole resistance business is pretty nice. Then we had circuits. We had different rules for circuits, right? We had the old series resistance, which was R1 plus R2 plus R3. We had the R total so this was series. We had the old parallel circuit, where we had the 1 over R1 plus 1 over R2 dot dot dot. And that was a slightly tricky one to use, but we've done all that and we're pretty good at it now. So, but we can still think a little bit about these circuits, and this whole unit that we're doing now, we really get into circuits and we get into more complicated circuits than you've looked at. So if we look at a circuit and we've got a couple of resistors here, I think we learned that if we had a voltage and we went round the circuit, we lost all our voltage. So if this is R1 and this is R2, two resistances, then we lose voltage as we go through the resistor, right? Now, we've learned that voltage, which we talked about just up here where you can't quite see, but we learned that voltage was the electric field times distance, right? So there's an electric field between the positive and the negative in here. So when we're looking at this, we've actually got an electric field. Put a stroke underneath that, just differentiates it from energy. So electric field times the distance gives us voltages. But the actual resistance, if we go back to Ohm's law, is equal to volts per amp. So what it's basically telling you is that it will lose a certain number of volts per amp. So if I have 2 amps flowing through here, and this is, let me say this is a 3, and this is a 3, then if I've got 2 amps, 3 ohms means it will lose 3 volts per amp. So if we had 2 amps flowing through our circuit, it's going to lose 6 volts, and that one will lose 6 because it says 3 ohms. That means it loses 3 volts per amp. Times 2 is 6 volts. So we'd know that this was actually 12 volts, right? So another way to think about the resistance. But what's actually happening when it's losing those? A lot of people like to describe it as obstructions. And so it's got energy. And normally what you'd find with a circuit, if you've got a voltage, we said volts is energy per charge. So when you say you've got 12 volts in a circuit, right? You've got this 12 volts up here, 12 volts, 0 volts. That means you've got 12 joules per coulomb, right? So 12 joules per coulomb means that's how much energy you've got. Now normally when we have, and I told you that voltage is like a height, so it's like how many joules per kilogram is a certain height, and we could have it that way. And remember I use that term GERS. It's like we don't have a word in gravity, but we have it in electricity, and it's volts. It's how much energy per charge. We're saying how much energy per kg. But when we let something drop in a gravitational field, it loses its gravitational potential and turns it into kinetic, and we get a big smack on the ground, right? In here, we've already worked out the electron flow when we looked at current, and we said, oh, they flow at about 1/4 millimeter per second, so not exactly doing a lot. Why are they not building up their kinetic energy? They're not building up their kinetic energy, even though they're losing potential, because they're smacking in to a whole bunch of other atoms and forces. And so this is the physical aspect of resistance. No resistance, when you go through a voltage, you just build up kinetic energy. When you go through a resistance, you don't. So hopefully we're making some progress with this whole resistance thing. If there's no voltage, there's no electric field, right? And no electric field, there's going to be no force acting. Let's now, so that's the basics of resistance that I want you to know. Let's just do a little mathematical thing with it now, where we say J equals current density. It's current per area. And I think we already looked at that and said that it was actually equal to NQVD. That's from our current little video that we did. Now, what we're going to say, current density is, you know, amps per area. This is area, amps per area. But we're going to also say that J must be proportional. So the amount of amps flowing has got to be proportional to something. We'll call it sigma times the electric field. It's proportional to the electric field flowing, right? So we've got these two equations here, and what we basically said is that current density is going to be the current per area, but we've also said current density is going to be proportional to the electric field. So we can equate these two guys, right? And we can say, but first let's remember something about the E, which is the, do we need to do a substitution for the E? I think we do. Remember, E equals volts divided by, you know, V equals ED, so volts per meter. So we can say current over A, current per area, is equal to sigma times volts per meter. I'll call it L if you like, just as a distance, a length. Now, what we can say then, and I think we've got to move it along a little bit here. Oh no, it'll give me a little bit more. I can upload videos a little bit longer than 10 minutes, so I think we're cool. So we've got this expression here. So let's solve this for V. We bring the L up there. So we get the L length times the current divided by A all over sigma equals volts. Now, we already had a expression V equals IR. So we've got the I here. So what we've basically done is we've said L over A sigma must be equal to R. So we've said, basically, that resistance is proportional to the length of the conductor. Longer wire, bigger resistance. Inversely proportional to the area. Thicker wire, less resistance. And inversely proportional to something called sigma. So what we actually end up doing is redefining sigma. And we redefine sigma as P. So if we say P equals 1 over sigma, right, then we can say resistance equals L over A times P. And so this sigma was a measure of conductivity, and P is a measure of resistivity. And basically, we've got some very high resistivity values, or very low resistivity values for things like silver. Resistivity equals 1.59 times 10 to the minus 8. That's a really little number. Look at rubber, look at silicone. It's a semiconductor, has about 640. Look at rubber, our insulator, has 10 to the 13. So there are, between 13 and minus 8, there's 21 orders of magnitude of resistivity. That's why I'm safe with rubber and I'm not safe with silver, a conductor. So a little bit on resistivity. That last couple of minutes, you didn't really have to know that, but the first 6 or 7 minutes, you did.